Hello, calculus fans. In this video, we will look at another numerical integration technique, namely Simpsons Rule. We will demonstrate how the technique can be used to approximate definite integrals, how to approximate the error involved in its use, and how the method is derived. Suppose we wish to approximate the definite integral from a to b of f of x dx. We can interpret the integral as the area under the curve y equals f of x on the closed interval from a to b. Simpsons rule uses parabolas on different subintervals to approximate the curve. In its application, the interval from a to b is partitioned into n intervals where n is an even number. Each interval is of equal width, namely delta x is equal to b minus a, which is the length of the interval, all over n. Then for a consecutive pair of intervals, namely the closed interval from x sub k minus 1 to x sub k, and x sub k to x sub k plus 1, the area under the curve on the interval from x sub k minus 1 to x sub k plus 1 is approximated by the area under a parabola defined by the 3 points of the partition and their y values on the curve, namely x sub k minus 1, x sub k, and x sub k plus 1. When parabolas are used for the xy pairs for 3 consecutive points of the partition, Simpsons rule gives the formula to approximate the definite integral. So the integral from a to b of f of x dx is approximately delta x, the width of any of the subintervals, divided by 3, times the quantity y sub 0 plus 4y sub 1 plus 2y sub 2 plus 4y sub 3 plus 2y sub 4, and that alternating pattern continues for those coefficients until we get to 2y sub n minus 2 plus 4y sub n minus 1 plus y sub n. Again, where y sub k is the function evaluated at the kth partition point. Let's see how we can apply Simpsons rule. Suppose we wish to approximate the definite integral from 1 to 4 of negative x to the fourth plus 10x cubed minus 33x squared plus 40x minus 13. If we use 6 intervals of equal width, the length of each subinterval is 1/2, and the partition is given by the points 1, 1.5, 2, 2.5, 3, 3.5, and 4. To obtain the y values, we evaluate the function f at the points of the partition, and so we can see where we get the point 1, 3, 1.5, 1.4375, 2.5, -1, and so on. And we can see in the graph how we divide up the interval from 1 to 4 and where those y values fall on the curve. We can also see how the different groups of the points of the partition are used to obtain the parabolas. For example, these first 3 points are used to define that first parabola. The points x sub 2 to x sub 4 give us the second parabola, and partition points x sub 4, x sub 5, and x sub 6 give us that third parabola. So when we apply Simpsons rule to the integral from 1 to 4 of negative x to the fourth plus 10x cubed minus 33x squared plus 40x minus 13, we get the width of the subinterval, 1/2, divided by 3, times the quantity 3 plus 4 times 1.4375 plus 2 times -1, and so on, so that our approximation to that definite integral is 0.875. So when 6 intervals are used with Simpsons rule, the area under our curve y equals f of x on the interval from 1 to 4 is approximately 0.875. The error estimate associated with the use of Simpsons rule can be calculated when we have an upper bound, which we'll call m, for the fourth derivative of our function f in absolute value on the closed interval from a to b. We will assume that the fourth derivative of f is continuous on this interval, so that the estimate for the error involved with Simpsons rule is less than or equal to m times the length of our interval, b minus a, to the 5th power divided by 180 times n to the 4th power. So in our particular case, for the approximation we just calculated, we can see that for our function f, the fourth derivative of f is -24, giving us a positive 24 when we apply absolute value, so that our error estimate, when we plug in all the different pieces, gives that our approximation of the definite integral is within 25 thousandths of the actual value. And we can also see that when n, the number of subintervals, increases, the error estimate will decrease, namely giving us a better approximation to the actual value. If you're interested in knowing how the formula for Simpson's rule is derived, we'll demonstrate that here. It's fairly intensive in the use of algebra. Recall that Simpson's rule is used to approximate the definite integral from a to b of f of x dx when the curve y equals f of x is approximated by parabolas on consecutive pairs of intervals, and where each subinterval is of equal width, namely delta x is equal to b minus a over n, and n must be an even number. The first parabola used in Simpson's rule is defined by the first 3 points of the partition, namely x sub 0, x sub 1, and x sub 2. When we consider the second parabola, it's defined by the points of the partition x sub 2, x sub 3, and x sub 4. And this continues until we get to the last parabola, which is defined by the last 3 points of the partition x sub n minus 2, x sub n minus 1, and x sub n. Let's consider a generic parabola that's defined by the points x sub k minus 1, x sub k, and x sub k plus 1, where, again, our y value, y sub k, is determined when we evaluate the function at x sub k. These intervals have equal width. X sub k minus x sub k minus 1 is the same as x sub k plus 1 minus x sub k, which we'll call delta x. And in our picture, the interval from x sub k minus 1 to x sub k plus 1 is twice the width of that subinterval, delta x. Let's consider the equation of the parabola that passes through the 3 points of the partition x sub k minus 1, x sub k, and x sub k plus 1, where the y values are found by evaluating the function at these points. Suppose the equation for the parabola is given as y equals ax squared plus bx plus c. We will perform some algebra to give us more information about a, b, and c. If I plug each of these x values into the equation for our parabola, I'm going to get these 3 different equations. Now remember, x sub k plus 1 is the same as x sub k plus delta x. So when I plug in x sub k plus 1 into my equation of my parabola, I will get this equation in blue. If I plug in x sub k into the equation of the parabola, I'll get this green equation. And if I plug in x sub k minus 1, that's the same as x sub k minus delta x, and I get this equation in red. I've got these highlighted in different colors because we will return to these ideas in subsequent slides. If I take the blue equation minus the green equation, that simplifies to a times x sub k plus delta x squared minus a times the square of x sub k plus b delta x. When I find the difference between y sub k and y sub k minus 1, I get a times x sub k squared minus a times x sub k minus delta x quantity squared plus b delta x. And when I take y sub k plus 1 minus y sub k minus the quantity y sub k minus y sub k minus 1, that all simplifies to 2 times a times delta x squared. So rewriting that same expression, but now simplifying what I have on the left, I get y sub k minus 1 minus 2y sub k plus y sub k plus 1 equals 2 times a times the length of the subinterval squared. And if I solve for a times the square of delta x, I get 1/2 y sub k minus 1 minus 2y sub k plus y sub k plus 1. And I've put this in a significant color so that I can return to it later. Now if I consider the area under the curve y equals f of x on the interval from x sub k minus 1 to x sub k plus 1, I get that definite integral is approximated by the area under the parabola ax squared plus bx plus c on the same interval, x sub k minus delta x, which is x sub k minus 1, to x sub k plus delta x, which is a x sub k plus 1. And I find the antiderivative, which is 1/3 a x cubed plus 1/2 bx squared plus cx, and I evaluate it at the endpoints and find the difference. So that when I evaluate that at the endpoints, I can see that I'm going to get a difference of cubes, a difference of squares, and c times the difference of those points of the partition. We notice that each of these terms has a factor of x sub k plus delta x minus x sub k minus delta x, which simplifies to twice the length of the subinterval, delta x. We're going to work with each of these three pieces separately and then combine them to simplify at the end. So when I work with that first piece where there's the coefficient of 1/3 a, we have that difference of cubes, which all simplifies to 1/3 times twice the length of our subinterval. And again, we see those pieces in blue, green, and red, and then purple, referencing what we've seen before, so that a sub x sub k plus delta x squared can be rewritten as y sub k plus 1 minus b x sub k plus delta x minus c. I can do a similar substitution for a x sub k squared, and again for a times x sub k minus delta x quantity squared. Simplifying all of that, I get that expression involving 1/3 a and the difference of cubes becomes 2 times delta x times 1/3 times the quantity 1/2 y sub k plus 1 plus 2 y sub k plus 1/2 y sub k minus 1 minus b x sub k minus c. When I work with the term involving 1/2 b, that all simplifies down to b times 2 times delta x times x sub k. And the expression involving c is just c times twice the length of the subinterval, which is delta x. Combining all those pieces, the area under the parabola on the interval from x sub k minus 1 to x sub k plus 1 is all simplified to be 1/3 times delta x times y sub k plus 1 plus 4y sub k plus y sub k minus 1. That's for a single parabola determined by 3 consecutive points of the partition. When we put the pieces together to approximate the definite integral from a to b of f of x dx, using Simpson's rule with n intervals of equal width, we get that 1/3 delta x times y sub 0 plus 4y sub 1 plus y sub 2 approximate the area under the curve on the interval from x sub 0 to x sub 2. 1/3 times delta x times y sub 2 plus 4y sub 3 plus y sub 4 approximates the area under the curve on the interval from x sub 2 to x sub 4. So just considering those partition points, I see that there's an overlap of y sub 2. And so that's where I see I'm going to get 1 y sub 0, 4 y sub 1, 2 copies of y sub 2, 4 copies of y sub 3, and so on. So that we develop the formula for Simpson's rule that the definite integral from a to b of f of x dx is approximated by 1/3 delta x times y sub 0 plus 4y sub 1 plus 2y sub 2, where we see that the coefficients 4 and 2 alternate until we get to 2 times y sub n minus 2 plus 4y sub n minus 1 plus y sub n. Again, where each y sub k is the function f evaluated x sub k, giving us the height of the function at x sub k. What are the key ideas presented here? Well, Simpson's rule is one of many numerical integration techniques. The formula is relatively easy to implement and is effective for approximating definite integrals. Keep in mind that any numerical approximation contains some error when comparing to the actual value. The error associated with estimating a definite integral when using Simpson's rule is given by the error in absolute value is less than or equal to m times the length of the interval, b minus a, to the 5th power divided by 180 times n to the 4th power, where n is the number of subintervals. Also, to apply this error formula, the fourth derivative of f should be continuous, and in absolute value, it's less than or equal to m for some upper bound on the interval from a to b. And finally, when compared to approximating a definite integral through the left, right, or midpoint rules, or the trapezoidal rule, Simpson's rule usually more closely approximates the definite integral.